In this and the next video, we'll state and prove the spanning set theorem. This theorem has two parts. We'll look at one part in each video. Okay. So the setting of the spanning set theorem is that V is a non-trivial vector space. By non-trivial, we just mean that it contains vectors other than the zero vector. And V is the span of finitely many vectors. And I should probably point out that not every vector space has this property. For example, the vector space of continuous functions is not the span of any finite set of continuous functions. But suppose the vector space we're looking at does have this property. Then part one of the spanning set theorem says the following. Suppose one of the vectors in this set is a linear combination of the others. Now, in the textbook, we're specifically assuming that the last vector in this list, V sub n, is a linear combination of the rest. But remember that sets are unordered. I mean, we can choose which of these vectors we write last. So the assumption that we're looking at the last vector is not really an assumption at all. Any vector can be the last vector if we want it to. So what the spanning set theorem, or part one of the spanning set theorem, says is you've got all these vectors, but one of the vectors is a linear combination of the rest. if we take that vector that is a linear combination of the others and toss it out of the set, that doesn't change the span. So in particular, the vector space V, which is the span of these n vectors, is also the span of these n minus 1 vectors. How do we prove that? Well, this is a set. This is a set. To prove that two sets are equal, we prove that each of them is a subset of the other. So let's, just for ease of writing, look at a set with some fixed number of vectors. But the proof doesn't change if we increase the number of vectors. This assumption is purely to make this easier for me to write down. And our assumption is that one of these vectors is a linear combination of the others, and we want to argue that kicking it out of the set doesn't change the span of the set. So we'll start by demonstrating that the span of V sub 1 and V sub 2 is a subset. Sorry about that if you're hearing background noise. We want this to be a subset of the span of V sub 1, V sub 2, and V sub 3. This is not difficult. Let's let B be the span in the span of these two vectors. That is to say that B is a linear combination of these two vectors. Then, certainly, we can add a zero vector without changing anything. So B is the linear combination of these three vectors. So B belongs to the span of these three vectors. And we've demonstrated that inclusion. The inclusion in the other direction requires slightly more work, but it's not massively more difficult. We want to show the inclusion in the other way. So we'll let B belong to this first set. And then demonstrate that this means B belongs to the second set. So if B belongs to the first set, it's a linear combination of these three vectors. Let me try to get both of these facts in our field of vision. V sub 3 is this linear combination of V sub 1 and V sub 2. So we can rewrite this as follows. We replace V sub 3 with this linear combination that it's equal to. And now, just as we run out of room on the page, we finish up our proof. We can distribute this and combine like terms. So that's A sub 1 plus A sub 3, C sub 1, V1 plus A sub 2 plus A sub 3, C sub 2, V2. So this vector belongs to the span of V1 and V2. So we have both these set inclusions, ergo we have this set equality, just as we wanted. In the next video, we will use the first part of the spanning set theorem to demonstrate the second part of the spanning set theorem.